going to do review on chapter 14. And you know, I got to looking at the review document that I have posted, and this is not the best one that I could produce. So what I'm going to do is I'm going to put this one up on the share. Let's see, let me pin video. I'm going to share the review document key, and then as we go, I may modify the problems to be a little more realistic. So just a word of warning.
Okay, and also I want to let you know I may not be able to stay on the whole time today, but I'll be able to watch the review
Yeah, it'll be recorded.
Okay. I just want to let you know I may have to get off about halfway through.
I'm a little better on turnaround time now too. I've got, I don't know if I told you guys, but I've upgraded my my computer equipment, and it's processing my videos a lot faster.
Okay.
So hopefully
awesome.
The turnaround won't be too much of a time lag.
Okay.
Okay, there's the review document that's in Blackboard. And the first thing I notice is here the signs somehow or other in the translation between the Word and Acrobat. It looks like the signs got shifted off. But I think I'm going to skip this one. I mean, I don't know why this was the first one, but this is a huge. This first problem is a huge strain on newcomers to chemistry. So we're going to move down the line a little bit. In fact, what I may do is come back to this one, because this one requires a substantial background to get it right. So we're going to come back to 2. Let's go to 3. And then we'll come back to that one later. Okay, number 3 says the rate expression for a particular reaction is, remember this is the differential rate law for a generic. Okay, so remember the construction of our rate law. We have a constant that I left out. There we go. A rate constant, the concentration of A to the first order, and the concentration of B to the second order. So what that means in terms of this problem, if the initial concentration of B is increased from 0.1 to 0.3, so it goes from there to there, what does that do to the actual rate, right? Doesn't change the constant. And we're holding this one steady. A doesn't change, but we're letting B change from 0.1 to 0.3. So the way to interpret this and to answer the question, if you're going to find out how much would the rate increase, you look at the difference between this and that one squared. So the easiest way, I think, is say, what happened to this one? Well, it increased 3 times, didn't it? From 0.1 to 0.3. But 3 times squared is 9. So that's what happens to the rate. The rate increases by 9 times when you have a second order increase of that much. If it was just first order, it would be 3 times increase, because everything is first order, just to the first power. Second power, you have to square it. Okay, so that was number 3. Let's go on to 4. For which order is the half-life of the reaction proportional to 1 over K? K is the rate constant, right? So let's make room here for number 4. So to answer this question, we need to take a look at each one of the half-life formulas, right? So for the 0 order, first order, second order. For the 0 order, the half-life is what? It's initial concentration of A over 2 times K. I believe that's right. I'm scratching my head. Let me see. This would be a good chance to check the useful information and see if I got that in there. Yeah. Yeah. Okay. And by the way, when you take the exam, I don't know, when you took the first exam, let me ask you a question. And you went into Respondus, was the useful information and all that other stuff that's extra, was it available to you in the browser?
No.
They shut you out, didn't they?
Yes.
Okay. So you
But
need to go
I
ahead.
did have it printed off.
Uh-huh.
So I had it with me there. So I did have the information printed off, but it wasn't available in the browser.
Okay. So that's going to be the pattern from now on. You have to have it ready for you before you go into browser.
Okay.
Yeah. So you've got, I know you'll have a periodic table and you'll have the useful information, and these formulas will be in the chart in useful information. They're not readily identified. I mean, they're just formulas that are stuck in there. So they have to know what they look like in order to use them.
Yeah.
Okay, so that's 0 order. First order is this one. And second order is, let's see, I think that's it. So one thing you'll notice is every one of these is proportional to 1 over K. Right? This one's 2 times K, but it's still proportional to the inverse of K in each case. So that lets us know that with this proportionality, 1 over K, all of them are proportional to 1 over K. That's why the answer is D. Let's see. I'll check these off as I go so I don't backtrack. All right. Okay, this is a fairly basic question, number 5. I didn't want to just jump into the deep end of the pool right off the bat. I want to get some, these are warm-up questions, so to speak, and then we'll get into the more difficult stuff after we get these things sort of firmly in mind. Okay, so 5. If the reaction 2 times HI yields H2 plus I2, and we're told it's second order, which of the following will yield a linear plot? Okay, so second order will give you a linear plot based on what relationship? Second order, remember first order is raw data, straight line. First order is natural log of concentration versus time. Will give you straight line. Second order is inverse. So the inverse of, let's see, what are our choices? HI. The inverse of HI concentration versus time. That's a straight line. Okay. And if you were to actually look at the plot, it would be like this, positive slope. So you would have inverse of HI equals K. T plus 1 over H. Initial concentration. Right? So what that tells you is it crosses the line down here. This is T, and this is, no, this is T, and this is 1 over. So if you know the slope, if you can plot it and determine the slope, then you got your K. And then in order to draw the line, you'll already have all of these values in here. And this one will tell you, say your data points start here and end here. So you got several of them in here. Wherever it crosses the line is HO. And you'll usually have that because that's when you start the experiment. But this is confirmation for second order reaction. Okay. All right, let's do 6. Scroll down. There's 6. All right. So 6 says we're basing question number 6 on that information preceding it. So we're referring to this reaction. 2A sub 2 plus B sub 2 yields 2C. I don't know how they, oh, because they're diatomic. That's why. So that's a diatomic element like oxygen O2 or iodine O2 or something like that. And then B sub 2 yields 2C. So that's the overall reaction. This is the reactants, those are the products coming out, and the reaction mechanism proposed fits in there. So it gives you apparently this whole reaction is slow, but one reaction in the mechanism is slower than the other. And it turns out that step 1, take one of these and one of those yields this one plus that. Now what's R? R is an intermediate, right? And it disappears in the next step. Like that. So because it's on the right here and the left here, it goes out, add these two together, and you get 2 of these, you get 2 of these, 1 of those. So the first condition for the mechanism is met. If you add the mechanism's reactions together, you should get the overall. That's first. If it doesn't do that, throw it out. The second is trying to determine the rate law based on the mechanism. Which one of these do you go from? Right? You go from the rate determining step, which is the slowest one. So the very slow is slower than the slow. And you would base your rate law on this one. And I think I showed in lecture that sometimes the form of the rate law determined by one of the steps is incomplete. Because if you have an intermediate in there somehow as part of your rate law, then that's not the end of it, because you can't have a reactant or a product in your rate law that is not in the overall reaction. So if that's the case, then you've got to do some manipulation and remove that somehow by substitution. And we're going to look at one of those in a few minutes. So the rate determining step is the step 1. It's always the slowest step that determines the rate. All right, that was 6. I'll come back to 7. That one's a little more involved. Let's look at 8 and 9 next. This is a graphic interpretation. Here we go. Be sure you understand what's meant. Now this graph is a little cryptic, right? Because it doesn't give you labels for the X or the Y axis. What the idea is that you would infer from the equation, from the question, what this graph represents. Okay. So if we got this representation, we have progress of the reaction down here, which is usually time. And then we have the energy of components at any one point in the progress of the reaction. Well, if we start off here, right, with our reactants, right there, then we add energy, right, so the reaction can proceed. It needs a certain minimum amount of energy. Right there on top of that peak. And this is the activation energy. Right? And the reactants are in a metastable state here. In other words, they could go one way or they could go the other. They have just a little bit of bump to the little more energy than required, they'll go on the other side. And in this case, they come down and they stop here. Okay? So, we've got various letters and lines on this graph, and one of them goes from here to there, and that's called A. Okay? Another one goes from here to here. That's called B. And then another one goes from here to the top. That's called C. And then we've got one in here that's kind of funky, like that. And that one goes from here to here, and that's called E. I skipped D. D is over here. Between there and there. Okay. Some of these are more important than others. This C is just the total amount of energy at that top position. When we're talking about activation energy, we're actually talking about the distance between where they started and the activated complex. Right, so A is the activation energy. Okay, let's look. Which letter shows the activation energy without a catalyst? And that's A. And then 9 says, which letter shows the activation energy with a catalyst? Well, the catalyst is going to lower the activation energy because it offers an alternate pathway for the reaction to proceed. You end up with the same products, and the catalyst is not consumed, but the catalyst is intimately involved in the reaction so that it offers that alternate pathway. And that's E. E sub A, catalyst. Okay, that answers 8 and 9. But while we're here, since we've got the activation energy without and the activation energy with, what do these other things mean? Well, I said what C meant. It's just the total energy from there to there, from some baseline here. And this is the amount of energy that the reactants have at the beginning, right here. We don't have one for this side, but if we did, this would be similar. It'd be the amount of energy that the products had at the end. And the difference between those two, this one and this one, is this one right here. And this is the change in energy. Well, actually, more often, rather than measure that value, which is difficult to get, we usually measure the enthalpy of the reaction. Now, what can we tell from this graph? That we put in energy, but we didn't get it all back, which means that the reaction is endothermic. We put in energy, and only some came back. If we had gone down here like this, we put in energy, and more would come back than we put in. That would be exothermic. Okay. Let's see. Yeah, let's go ahead to 10. Let me mark off these two guys so I don't backtrack. And we'll look at 10. Oops, there we go. All right, for number 10, I probably don't even need to put it on the board. I could annotate this one. And let's use circle. Okay, for this reaction, the following mechanism is proposed. This two-step mechanism. Doesn't say which one's fast or which one's slow, because that's immaterial to the question. The question is, where is the catalyst? Okay. The catalyst is something that goes in the front, looks like a reactant, and comes out the end as a product. So it goes in, comes out, it appears macroscopically to be unchanged. So we look for one that does that. And it looks to me like that one starts in there and it comes out right here. So iodine, the iodide ion, is the catalyst in this reaction. That's one proposed mechanism. I think actually they've discovered the mechanism for this reaction where hydrogen peroxide is decomposed catastrophically with iodide ion. And I think I showed that to you guys in the lecture. What do they call it? Something toothpaste. Dragon's toothpaste, where they colored it and it comes out big foamy.
It's elephant toothpaste.
Elephant, thank you. Elephant
You're
toothpaste.
welcome.
This was the reaction. But I think they've determined that this is not the mechanism. It's actually 4 steps. But for argument's sake, iodide goes in, comes out. That's the catalyst. Now, is this a heterogeneous or a homogeneous catalyst? Well, we know from the video that both were in solution, like the hydrogen peroxide in the bottle or the graduated cylinder and the iodide that was added, they were both in solution. And in fact, even if you add the solid potassium iodide to the hydrogen peroxide, it won't react until it's in solution. So the potassium iodide goes into solution first, then it reacts. So the catalyst itself is homogeneous with the reactants. All right, so that's 10. Let's see if we do one of these others before we come back. Yeah, let's look at 13. And let's see, I'm going to have to, oh, I know what's wrong. Whenever I use the annotate, I got to go back and click on the mouse. Now, my mouse is activated again. That's why I don't like that annotate so much. It's really clunky. Oops. And I forgot to, let me see if I can do this with my keyboard shortcuts. Nope. I got to annotate and then erase. And then go back to the mouse. Okay. So here we have 13. Let's see. I scroll too far. Let me go up just a little bit. There we go. So we've got this same reaction we were looking at earlier. 2A sub 2 plus B sub 2 yields 2C. And there's a mechanism. Now, according to the collision theory, what should happen? Well, when A sub 2 encounters B sub 2, two things have to be present, right? You have to have enough energy, activation energy, but you also have to have orientation. They've got to be oriented properly so that the bonds can break and reform for the products. Well, all this question asks is, in the activated complex, in order to produce C, two of these C's, A, maybe I better draw it. We've got A bound to A and B bound to B. When they come together, they form a metastable activated complex. Okay. So when they break apart, they'll be able to produce two C's. Right? It doesn't tell us what the C is, but which one of these would be most likely to resemble the activated complex would be this one that I just drew, the B. And notice this is kind of squirrely here. This A refers to that one right there, and this B refers to this one, and C refers to that one, and so forth. The way Word works, I can't get that C to go up here in line with the picture. Or I can't get the picture to drop below the line. Not the way I constructed it as a word list. Anyway, the intermediate then would just be that, where you're starting to break these bonds and you're starting to form those bonds. So my guess is that C is going to be some combination like AB together equals C. Okay, so that's 13. Let's see. Let's go ahead to 14. That's a generic question. It doesn't require calculation. Oops, there we go. Which of the following statements about enzymes is incorrect? Okay. Remember, we referred to enzymes as a biological catalyst. And in many respects, it is. It causes reactions that would normally proceed very slowly to proceed very rapidly. But enzymes are really more than that. And let me see, I'm not sure if this question addresses those differences or not. Which of the following is incorrect about enzymes? All right, they are proteins that catalyze specific biological reactions. That's true. They do just that. Several hundred are now known. Okay, well, when this question was formulated, yeah, my guess is it's in the low thousands now, well over 1,000. But as far as it goes, that is a true statement. The molecules they react with are called substrates, and that's true. This is terminology from biochemistry. The substrate is acted upon or one or several substrates are acted upon by the enzyme. That's true. They are equal to inorganic catalysts in efficiency. That's false. In fact, inorganic catalysts are very inefficient, whereas enzymes are extremely efficient in the mediation of biochemical reactions. They really have to be in order to make the cell function properly. They've got to be very efficient. And in addition to that, they are controllable. In other words, enzymes can be activated and deactivated by other additives or other compounds that are produced and controlled by the cell environment and the nucleus. Right? So enzymes are, at their base level, are catalysts, but they're really more than that. And typically, even though reactions can proceed forwards and backwards using enzymes, catalysts, yeah, definitely, you get forward and reverse reactions fairly easily. But enzymes are a little more difficult in that respect. They generally catalyze a forward reaction almost to the exclusion of any reverse reactions. So if you need a reverse reaction, you need a different enzyme, and that's usually the case. You get one enzyme to go one direction and one to go to the other direction, and that makes sense because the cell needs to maintain control of those reactions. And if it doesn't have control, if the enzyme can go forwards or backwards, then it loses some of that control. So most biochemical reactions have a forward enzyme and a reverse enzyme. Okay, so that was 14. Let's see. Let's see. Okay, I'm going to skip 15. Let's do 16. Now we're going to get into some calculation. Here we go. 16. So we've got room here. Yeah, this should be enough room if I stay on this middle board. I don't need to use the expansions. Okay, so for this generic reaction, okay, we start off at a concentration of 4.2 molar for the A. So the concentration of A at time 0 is 4.2 molar. This looks familiar. Did we do this in class?
I think we may have, or something really close to it.
Okay. Well, I'll do it again. So we'll have it on record here for this video. So this is our starting condition, right? At time 0. The first 2 half-lives are 56 minutes and 28 minutes. So what does that mean in terms of the progress of the reaction? That's what we're aiming at here to answer the question and find out what K is. Okay, so the first half-life is 56 minutes. So after 56 minutes, we'll have half of that. Okay, that's the first half-life. Second half-life is 28 minutes beyond that. Remember, half-lives, you can pick the starting concentration. So now the starting concentration for the second half-life is 2.1. And at the end of another 28 minutes, this concentration is now 1.05. Correct? It's half of that, half of that. But the time from T0 is 28 plus that, right? This is 28. So this would be 84. Okay? 84 minutes. Okay. So since we have half-lives here, let's use half-life formulas to tease information from. Maybe I should have. Okay, I'm going to move over here and add that half-life discussion. Okay, so for these, we have 3 choices. 0 order, first order, second order. So for 0 order, what's the half-life formula? It's initial over 2K. For second order, first order, excuse me, the half-life formula is 0.693 divided by K. And for the second order, T1/2 is 1 over K times initial concentration. Okay? So we're trying to lighten the load, right? Can we eliminate one of those as a possibility? Then we know it's not that order, it's maybe one of the other two. Notice that the half-life here changes with concentration. This concentration means the half-life is that much, but this concentration means the half-life is that much. So the half-life does depend upon the starting concentration. That one does, and this one does, but that one doesn't. So we can eliminate first order right off the bat. This is not a first order reaction. Okay, so what's next? Well, now, if we put the starting concentrations in and we put the half-life for that starting concentration and calculate K for both of these half-lives, then the one that wins is the one where K does not change, because K is a constant, right? If K is different for one than the other, then we know it's not that one either. So let's do the first one. And the first one would be starting concentration of 4.2 divided by 2 times 56 minutes. Oh, wait a minute. That's not right. Sorry. That's a K. 56 minutes goes over here. So now we solve for K, right? So I'm going to need my calculator to do that. All right. So if we put K over here and put 56 over there, I just swap places, then K is going to be 4.2 divided by 2 times 56. Okay? And K is, let's see, 4.2 is 5.7 times 10 to the minus 1, or 0.57. 0.57. Okay? Now I have to make room. So the other one, we have starting concentration of 2.1 and 28 minutes. So 28 minutes is the half-life for a starting concentration of 2.1 molar divided by 2K. So now K is equal to 2.1 over 28 times 2. Let's see what that is. 2.1, 8, 2 is 0.0375. Okay. They're different K values. So it can't be zero order, right? It has to be second order. Now, if you're taking a test, well, it's asking us for what's the K, so we do have to calculate it. And so we'll go over here and we'll work on second order. Right. So second order says that the T1/2 is equal to 1 over K times the initial concentration. Okay, so now we'll just do the same thing for each one. We'll plug in 56 minutes equals 1 over K times the initial concentration of 4.2. And then we'll calculate K. K would be, just swap places, this one over here and that one over there. So 56 times 4.2 reciprocal, because it's in the denominator. Which is 4.25 K equals 4.25 times 10 to the minus 3. Now we'll take the second one. 28 minutes equals 1 over K. And the initial concentration is 2.1 now. So K, bring this over here, that one over there. 28 times 2.1, take the reciprocal. That didn't work. Did I do something wrong? Well, I must have done something wrong. Let's go back and check my work. 4.2 starting. 56 minutes, the first half-life. Starting 2.1 for 28 minutes, and you get, did I do this one right? 2.1, take a half of it. Yeah, that's right. So that concentration did I use the right formulas? Yeah. Okay. Zero order. 2K. That's the right formula. See if I did my calculations correctly. 4.2 is initial. 2K is unknown. 56. Yep. Okay. So take K over here, 56 over here. 4.2. 3 divided, 56 divided. Oh. I didn't calculate right. Let me do it one more time. 4.2 divided by 2 divided by 56. 0.375. Okay. So that one should be wrong, right? I had a K value over here, which is, if I still have it in my, I don't have it in there. Let me just calculate it again. 28, 2.1, reciprocal. This is 1.7 times 10 to the minus 2. So that one's wrong. And this one's right. It's a zero order reaction with 0.375. And rounding error says it's, the nearest one to that is C, 3.7 times 10 to the minus 2. So it was a calculation error right here. It's my fault. Whoa, okay. Close quarters in here. All right, so that was 16. Okay, let's see. Is anything beyond 16? Or we can back up now. Oh, there's 17. Yeah, let's do 17. We're getting into a little more calculation. I mean, it looks really, it looks like a monster, doesn't it? Actually, it only goes down to there, right there. This data set provides information to answer that question. But remember about these, about word problems, they are designed specifically to confuse. Let me start over here. Be sure I'm on camera still with this. Oops, go back this way. There we go. Okay, so 17 says, for this reaction, 2 N2O5, dinitrogen pentoxide, yields 4 nitrogen dioxide plus oxygen. And then we get this data set. For time, right, each time interval, we measure the disappearance of N2O5. Right? Okay. What we want to know is what was the initial rate of production of NO2. Right? So this is at least 2 layers. What do we know about the rate? We really only know the raw data says disappearance of dinitrogen pentoxide. But look at the balanced equation. If we lose 2 moles of N2O5, we produce 4 moles of NO2. Right? So the rate of production of NO2 is twice the rate of N2O5. Right? 2 to 4, 4 to 2. 4 to 2 is 2 times. So if we determine the rate of disappearance of N2O5, we should be able to calculate the rate of appearance of NO2. And the initial rate would just be this 0 to 10 minutes. Okay? So rate is going to be, and this is rate of N2O5 disappearance. Oops, I don't need 2 P's. Disappearance. Okay, so we calculate that by change in concentration over change in time. Okay. So we're going from, actually, it would be a negative value, 0.92 times 10 to the minus 2 minus 1.24, which was the initial, times 10 to the minus 2, and divided by how much time does that take? Well, the final time was 10, initial time was 0. So we just divide this difference by 10. And since they're both to the power of 10 to the minus 2, we can keep that. That stays right over here. And we find out 0.92 and 1.24 is 0.32 divided by 10. So that's 3.2 times 10 to the minus 2. Let me see if I did that right. Let me do it the long way. How about 0.92 and just put in the exponent. Right, enter. And then subtract 1.24 exponent to change sign. Okay, and then 10. Yep. Good thing I checked myself. So actually this is a negative. And this is for the disappearance of N2O5. But for the appearance of NO2, it's a positive, right? It shows up. But there's twice as much of that. So that would be 6.4 times 10 to the minus 4 molarity per minute. Okay? If I did that right, and it appears that I did not, for this reaction is approximately we do that again. See if I got my numbers right. 9.92, 10 to the minus 2, yep. And 1.24, okay, yep, that's right. And 10 minutes, that's right. So did I do my calculation right? Or maybe the answer's wrong. Let's see. 0.92 exponent. And 1.24 exponent. 2 times 9. Yep. And then 10 divided. So that's the disappearance of N2O5 and the appearance of NO2 is double that. Should be 6.4 instead of 7.4. Let me see if I caught it in my, let's see. Oh, I took a different approach, didn't I? Okay. Okay, I see. All right, that's a good point for discussion here. This delta concentration over delta T, that is over an extended period of time. 10 minutes, that's a long time. So over that time, this was the rate of production of NO2. But the question asks for initial rate. What is it at the instant the reaction starts? Right? So rather than this average rate, what it really wants is the instantaneous rate. Right? And you can't determine it this way. You have to go back to the rate law. Find out what rate is it? What rate law applies? And that's a little more than I would impose on you guys for an exam, because it takes a lot of work to determine which one. You have to determine natural log and reciprocal data set and plot them. And if you do that, you find out that it's first order. So what I would do is I would say in this first order reaction, right? So you know off the bat that it's first order, and you know which one of the plots is valid, natural log. You would also need to know K. All right, so if we know it's first order, let me go back and let's do it right. Oops. All right, if you know it's first order, that means it's the natural log. So we have the natural log of N2O5 is equal to negative KT plus the natural log of the initial. There we go. Okay, so that would be determined by plotting the data. Right. Right? So if you were doing this, well, you will be doing something like this for the lab on kinetics. You actually have to plot the data for each transformation. Raw data, natural log, reciprocal. Once you have that relationship established, then all you have to do is plug in values. So the initial concentration here is 1.24 times 10 to the minus 2. Okay? And the time interval, I think I used 70 minutes, right? Now that we have a straight line, right? Now that we have a straight line, we can use the whole data set. So we could go down to 70 minutes here. K is unknown. And then what is the final concentration? 0.15 times 10 to the minus 2. Right? And then we solve the equation and we find out the value of K. And K is 3.02. Times 10 to the minus 2. Okay? All right, then we go back to the initial rate law. So the rate law is going to be the rate here is equal to K times the concentration of N2O5 to the first order. So there's your rate law right there. So what is the initial rate? Well, what's the concentration at the very beginning? At the very beginning, the concentration is 1.24 times 10 to the minus 2. And K is this value, 3.02 times 10 to the minus 2. Yep. So the rate of disappearance of N2O5 at the beginning is these two numbers times each other, which is 3.74 times 10 to the minus 4 molarity per minute. Now, what's double that? That's the rate of disappearance of N2O5. What's the rate of appearance of NO2 is twice that. So this is where you get the double 3.74. .5 or 7.48. Okay. I guess so the moral of this story is read the question. What does the question say? The initial rate of production. When they say the initial rate, that means what it is at instant it starts. And that's it.
Dr. Blah, I'm going to get ready and get off here real quick.
Okay.
All right, but I'll watch it. Thank you.
Okay. Bye-bye. Have a good weekend.
You too.
Okay, that was 17. Where's my pen? It's in my pocket, of course. That was 17. And let me mark that off so I don't backtrack. 17. 18. Okay. We'll go to 18, then we'll go back to some others. Now we're gonna look at mine's gone blank. Arrhenius. We're gonna look at Arrhenius equation. Actually, I think we're gonna use Arrhenius integrated version of the equation. And you may notice that in the exam folder where you have those useful information documents, if you go in there and look at the table, let's see, what does it look like? Here it is. The one that looks like this. There. You'll notice that the Arrhenius equation down over here, this missing a 1 over the T2 temperature, right? That's an artifact of translation of a Word document into Acrobat, the Adobe. You just somehow just drop that 1. So if that's not there, be sure and put it in for your own benefit, because it's supposed to be the reciprocal of T2. All right, with that being said, let's go back to 18 and use Arrhenius equation. Let's scroll down to 18. Here we go. Oops, too far. There's 18. Okay. So the equation, the question is, if the temperature changed, well, let's see, are we basing it on, yes, we're basing it on this information up here. Right, so question 18 refers to the information contained in this statement. The rate constant K for the reaction shown below, right here, is 2.6 times 10 to the minus 8. When the reaction proceeds at 300 K. And at that point, and we have to assume the activation energy is not significantly changed over that temperature range, right? We have to assume it's constant. The activation energy then is 98,000 joules per mole, or 98 kilojoules per mole. And the universal gas constant is here. You'll need that. Okay, if the temperature changes, number 18, from 300 to 310, another 10-degree change, remember, kind of like that rule of thumb, except, remember the rule of thumb says if the temperature changes by 10 degrees, the rate of the reaction doubles. So don't let that fool you, because that's only under certain specific conditions. In this case, you're given the activation energy that will determine that ratio. So the rate constant would change if you change the temperature from 300 to 310. The question is, what's the ratio of the K values from 310 in the numerator and 300 in the denominator? The K for 300 in the denominator to the closest whole number. Okay, so here's the approach. 18. I probably better start over here. Give myself plenty of room. All right. So we know we're gonna compare two rate constants at two different temperatures. So we need the Arrhenius equation, the integrated version. And the integrated version is natural log of this ratio K at the higher temperature divided by K at the lower temperature equals the activation energy, which we assume does not change over that temperature range, and then times the difference of the temperature at the low end minus the temperature at the high end. Well, actually, the reciprocal of the temperatures. Okay? So the K2 is going to be the K for the higher temperature. So we'll write it in like that. So this K at 310 divided by this K at 300 equals what? Well, the activation energy is 98,000 joules per mole. Notice when I put this question in that set, I gave you the activation energy in joules per mole, just so that there wouldn't be a mistake. I mean, if I were tricky, I'd call it kilojoules, and then you would have to change it to joules. Why? Because the constant R is in terms of joules, right? The units have to, excuse me, the units have to match. So I was kind enough to give it to you in joules already. And then R is 8.314 joules per mole K. All right. And then the temperature, the high temperature is 310. And the low temperature is 300. Okay. And there, I was kind enough again there to give it to you in K. Right? If I'd have been tricky, I'd have said, I'd have given it to you in centigrade, or even worse, I'd have given it to you in Fahrenheit. Then you would have to go through and change it to C, and then change it to K. Right? But we don't have time to do that. Okay, so there's the equation. Now, is that going to answer our question? The question is, what's the ratio of K310 to K300? Here it is right here. That quotient is your unknown, right? So you just keep that together and solve for that quotient. Right? So all of this taken together all of this taken together is equal to 1.2675. In the interest of time, well, why don't I do it? I might as well. We've got a little time. So let's say 300 reciprocal, and then 310 reciprocal, and subtract them. And then times 98,000 and divided by 8.315. 314. 1.267. Okay, it agrees. All right, and that's equal to the natural log of K to the 310 divided by K to the 300. K sub 300. There you go. All right, so we want that ratio. So we need to resolve that log transformation in terms of this value. Right, so you remember how logs work. You've got a base of E here. This value is equal to E to that power. So on your calculator, you would put that in as the power of E, right? Let's see. I'm looking, there it is. On my calculator, it says E to the X. And that's what you would use for this. In that case, if we do that, let me just do that. E to the X. It should be 3.55. Right? To the nearest whole number, it says. So rounding, right? You round up. Nearest whole number is 4. That's why the answer is D. So even though it's got all that blue smoke in there, and there are values in there that you can use, it told you the rate constant at one temperature, but you don't need that, right? Because the question asks for the ratio. Right? So this ratio is 3.55. We can calculate the rate constant for 310. All we have to do is plug in that K value that's given, 2.6. Let's just do that. So K to the 310 is actually K to the 300, which is 2.6 times 10 to the minus 8, right? 2.6, yep, times 10 to the minus 8 times this ratio number. Let's just see what the value is. 2.6 exponent 8, change sign, 3.55 times 9.23 times 10 to the minus 8. So that's the new rate constant at the new temperature, right? And with an activation energy of 98,000 joules per mole, you don't get the rule of thumb that's increase the rate of reaction twice. We increase the rate of reaction 3.55 times. All right, that's number 18. Let's see, mark that one off. And let's see. Oh, that's a good one. Number 20. I think 20 is the last one. Yeah, and then we'll go back and work some of those that I skipped. Okay. So let me make room here, erase this one out. I'm going to try to stay on this center board because it doesn't have as much ghosting for this one. 20. All right, so let's scroll down to 20. Here we go. The first order decomposition of hydrogen peroxide at minus 30 degrees Celsius occurs with a half-life of 42 seconds. What will be the residual concentration of 10.2 mole per liter hydrogen peroxide after 3 minutes? All right, so we got to break this down. What will be the residual concentration? That tells me that you need the integrated rate law because that incorporates this time factor, 3 minutes. Okay, whereas the differential rate law is not appropriate for answering this question. But we'll also need the half-life formula. And fortunately, we're given the order of the decomposition. It's first order. So what's the half-life formula for first order? Right there. Okay. So we're given the half-life, right? It doesn't matter what the concentration is. We can solve for K. And then K will go into our integrated rate law. And we can solve the rest of the problem. So we need to know the half-life, which is 42 seconds. Okay. So we'll solve for K. Right? K goes over here, 42 goes over there. So I'll probably ought to write it in. 693 divided by 42 seconds. Okay, 0.693, enter, 42 divide 1.65 times 10 to the minus 2. Okay, now we need the first order integrated rate law, right? Zero order is raw data. First order is natural log. So we go back to the natural log equation. Right? The natural log of concentration of hydrogen peroxide equals negative KT, let's see, plus the natural log of the starting concentration. There we go. Right. Okay. So one thing I want to point out here, we determined that K in terms of seconds. Right? So this is reciprocal seconds, right? Because it's in the denominator. So that means when the problem asks for 3-minute time interval, how many seconds is that? 3 times 60 is 180. So this is 180 seconds. Okay, and then our K value, which is 1.65 times 10 to the minus 2 reciprocal seconds, right? So the seconds cancel. And there's a minus sign. And then the initial concentration is what? If you're starting at, what will be the residual concentration of 10.2 mole per liter after 3 minutes? So that's our starting concentration, 10.2 molar. Okay, now we just have to solve for that term. Okay, so we take the natural log of this, multiply those together, add them up. 10.2 natural log. Right? And then we do 1.65 exponent to minus and 180 times. And then we add those two numbers together. And I get 1.65 times 10 to the minus. Really? Is that right? No, that's not right. I must have done something wrong. Let me do it again. Constantly checking myself. Let's do this concentration first. Did I put those numbers in right? 1.65, 10 to the minus 2. Right? Yeah. So this times that is what? This is 2.97. No. Yeah. 2.97. And the natural log of 10.2 is 2.32. See, I knew I did something wrong. Let's see. Where am I? Oh, negative 2.97. And this is minus, I'm going to write it standard notation, 0.6476. And that's equal to the natural log of our concentration. So we just need to take this as the power of E. 5.2 times 10 to the minus 1, or how is our answer given? It's given in standard notation. So 0.523 is what I got. Concentration of H2O2 after that much time is 0.523 molar. Okay? So easy to get sidetracked, so easy to make mistakes. Constantly think about what you're doing. Does it make sense at each step? So that was 20. Now we can backtrack and pick up those more difficult problems. We're going to go back and I know we're going to pick up initial rates problem. Let's see. Let me mark this one off. Okay. Now let's go backwards. Skip that one. How about this one? $12. We'll come back to 12. We'll do 12 last. 7. We might do 7. Number 2. That's a good one. So let's go back to number 2. This is going to be using the method of initial rates to determine the rate law and the K-value. Well, actually, it doesn't do the K-value, but I'm going to show you that anyway. Let's see. No, that's one that's too far. Here we go. All right. So there's our data set. Right. Here's our balanced overall equation. Right. And the first thing you'll notice about that is the charges don't balance. Right. 2 times 2 plus on this side is 4 plus. But you got 6 plus on this side, plus you got 2 minuses. Right. So the charges don't balance. I would suspect that the spectator ions have been removed from this reaction. Right? So it's balanced for the reactants and products that are involved in the reaction, and the spectators are gone. They just get in the way. So the data for each one of these experiments, that one, that one, that one, and that one. And let me annotate those. I think this is one time where annotation might be useful. Text. Okay, so let's make this one Roman numeral 1. Let's make this one Roman numeral 2. This one Roman numeral 3. And this one, excuse me, there we go, Roman numeral 4. Right. Now I need to, nope, I don't want to do that. Let's go back to mouse. No. Select. Yeah. What I want to do is move these guys. There we go. Make them pretty. I got time. And this one. There we go. Okay, so now we have each of our experiments, Roman numeral 1, 2, 3, and 4, identified. And we can, it's easier to discuss them that way. All right. So first thing you do when you're presented with this type of problem, where you need to determine the rate law for a reaction in which you're given method of initial rates. Method of initial rates is going to have several experiments. These are independent experiments, each one of these. Well, they're on the same reaction, of course, but they have different concentrations. So they produce different rates of reaction. Initial rates at the very beginning. And my guess is that these initial rates are determined as best they can early on, as early as possible in the reaction. Why? Because you don't want competing reverse reactions interfering with the rate. You don't want a combination of forward and back. You want only forward. So you do it at the very beginning. Okay. So in order to write this rate law, we need to write the generic rate law first. And for that one, it will be, let's see, this is number 2. Number 2, the generic rate law is just the rate equals the concentration of MnO4 minus to some power, N. That's the order of that reactant. Then we have H2C204, which is H2C204. I think that's oxalic acid. To the M. You ever seen the oxalis growing on a hillside? It looks like little tiny clover leaves, right? But they usually have a yellow flower. It's a type of wood sorrel, if you want to look it up and learn about it. But if you take those leaves and just stick them in your mouth and chew on them, they're very sour, right? It's because of that oxalic acid. Okay, and then this one is proton, hydrogen, to the L power. Okay, so now, oh, I left an important part out of this whole thing. K, the rate constant. Now we have our generic, and we need to find out what is the value for each of these orders, right? So the way to do it is you take a pair of reactions and you set up the rate law here in terms of those rate reactions, filling in the values for each one of these, and you choose them in such a way that, in this case, 2 of them are the same for both experiments, and only one of them varies, right? So if we want to find the rate, the order for the manganate ion here, we want it to change, right, between 1 and one of these others, but we want these 2 to stay the same. And it looks like the first 2 are ideal candidates. So next thing you have to do is, since we're going to fill in these rate laws and we're going to make a quotient out of those rate laws, put one on top, one on the bottom, and divide one equation into the other. So it simplifies things if you make sure that the rate of the one on top in the numerator is bigger than the one on the bottom. That way you get a whole number or a fraction greater than 1. So we're going to put 2 on top of 1. Like that. Okay? So we just fill it in like this. So what's the rate for 2? The rate for 2 is 8 times 10 to the minus 4. Right? And the rate for 1 is 2 times 10 to the minus 4. Now, the second one is across here. With its n value, and these others, H2C2O4, M, and protons to the L. And the one experiment, similar. I'm going to fill in numbers in a minute. I just wanted to make this point. Okay, so now we can put values in here. So this one on top is the second equation, 2 times 10 to the minus 3 molar. 2 times 10 to the minus 3. And the one on the bottom, I think, is 1, isn't it? 1 times 10 to the minus 3. All right. This one is 1 times 10 to the minus 3. And this one is also 1 times 10 to the minus 3. Hydrogen ions, 1 and 1. Okay. Now, this is going to tell us the order of the manganate. Because these two, identical, identical, same, 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 same. That means you're only left with this one and that one. So this number divided into that number is 4. Right? And this one has that to the n power divided by this to the n power. And in math, that expression is the same as right there. It's exactly the same. This one here is the same as that one. So this is what? 2 to the n power equals 4. So what's n? N has to be 2. Squared. 2 squared is 4. Okay? We got our first one. So now we can say that one is 2. All right. So let's make room for the next one. Okay. Pick an experiment, a pair of experiments in which the oxalic acid changes, but the other two components stay the same. Right? So both of these up here are different than both of those. So we just need to say, okay, it looks like if we do 2 and 3, this one stays the same, this one stays the same, and that one varies. And again, 1.6 times 10 to the minus 3 is bigger than 8 times 10 to the minus 4, so we'll put 3 on top. And, 2 on the bottom. Okay? So now 3 is 1.6 times 10 to the minus 3. And the bottom is 8 times 10 to the minus 4. Okay? Now, we're focused on this one, aren't we? So let's put those values in. 2 times 10 to the minus 3. And 1 times 10 to the minus 3. Okay? Now, we chose the experiments so that this one is equal to that one. And that one is equal to that one. So we just cross them out. We don't need to write it in. Now, what is this? This is 1 into 2, which is 2. 10 to the third, 10 to the third, out to the M power. What's this one? Well, we've got different powers of 10. So in order to do that in our head, we've got to make the transition, right? So what would this be 10 to the minus 4? That would be 16 times 10 to the minus 4 over 8 times 10 to the minus 4. So that would be 2. Now M is equal to 1. Okay? So now we've got M equal to 1. One more, and we've answered the question, but we're going to go one step beyond that, like I said before. Right? So that one, this one's going to stay the same, and this one's going to vary. So this one will cancel out, and we're focused on that one. Right? So which two experiments will give you that one? Where the third component, the protons, vary. Right? So it looks like any one of these three versus the last one. Right? So the last one's going to be in there, Roman numeral 4. And then we got to be sure that these stay the same. Right? So we could use this one, we could use that one. So let's use 4 and 3. Right? This one stays the same, this one stays the same, but that one varies. So if we use Roman numeral 4, I'm going to go bouncing back and forth with my markers. And 3. Now we need to change this value and that value. So the rate for 4 is 1.6 times 10 to the minus 3. And the rate for 3 is also 1.6 times 10 to the minus 3. And the concentrations over here are 2 on the top, 1 on the bottom. So now this resolves to 1. All right. And this resolves to 2 to the L power. Okay. What does L have to be to make 2 into 1? L has to be 0. Anything to the 0 power is 1. Okay? So now we've got our values for order. Make room for the next step. This actually answers, well, it doesn't answer the question yet. Okay, I'll show you why. When you write this rate law, that one is to the second power. This one's to the first power. That one's to the 0 power, which means what? It means it disappears. It's not even in the expression. Right? 0, anything to 0 power is 1. So the rate equals whatever the K value is, MnO4 minus squared H2C2O4. We don't even write the 1 in. If there's one of them there, it's 1. So that's the rate law. And that's why the answer is D. Because with the 0 order for hydrogen ions, they drop out of the expression. You don't even need them there. Okay. Now, let's say we want to find out what K is. How do you do that? Well, you've got the orders. We've got concentration values, and we've got rates, right? So K can be one unknown. Just pick any one of those experiments, right? Let's make it easy on ourselves. Let's say this one is, let's say experiment 1. What's the rate for experiment 1? 2 times 10 to the minus 4. Equals K times concentration of manganate, 1 times 10 to the minus 3, squared. Don't forget that. And then oxalate or oxalic acid is 1 times 10 to the minus 3. 1 times 10 to the minus 3. Okay. Now we solve for K. So K is going to be 2 times 10 to the minus 4 divided by this expression, 1 times 10 to the minus 3. What's this one? Right, the same base. That one is squared and this one's the first power. It's the same as this one to the third power, isn't it? That's math, right? 2 plus 1 is 3. Makes it easier. So let's take that one. 1 exponent 3, change sign, and then we'll take this one to the third power. Oh, that's easy. Why didn't I think of that? 3 times 3 is a minus 9. So this is 1 times 10 to the minus 9. Divided into 2 times 10 to the minus 4. So that's 2, let's see, 2 times 10 to the 5th. All right, so that's our K. It wasn't the question, right? But I figured while we were here, I'd show you how to do it. All right, so that was number 2. Number 2. And we've got, how much more time? 13 minutes. Let me see if there's one in here that we can do in 13 minutes. It's a choice between 7 and 12. Let me see. I'm gonna look at my worked problems and see which one takes the most time. Let's do, what did I say, 12? Yeah, let's do 12. I think 12 will work out a little smoother. We need smooth right now because confusion is not the right way to go. So let's go down to 12. Okay, I need my mouse back. Here we go. Oh, I got to get rid of, I got to do some erasing here. There's my eraser. There it is. I annotated, forgot to erase. There you go. Now we'll go down to 12 as soon as I get my mouse back. There we go. Oops, too far. Scroll up. There we go. Okay. So let's make room for 12. And that should finish out the day. All right. Let's see, how much room am I going to need? Yeah, I better use the whole board. 12. All right. So the question is, we've got this overall reaction. We've got 2 O3s, which is ozone, yield 3 O2s, which is what we consider normal oxygen. So we got this one, 2 O3s, And it looks more like a 20, doesn't it? O3. I'm gonna leave the gas out. And that yields 3 O2s. Okay. The proposed mechanism is this one. O3 O2 plus O. And then the second step is O3. Excuse me. O3 plus O. So we're adding this intermediate here. Yields 2 O2. Okay? Now, what can you deduce from that at this point? When a mechanism is written this way with double barbs, what they're saying is that it's a fast equilibrium. This is the fast step. This is the slow step. Right? That's not given information, but it can be deduced from those things. So we would say this one's fast and this one is slow. So our rate law should be written based upon this reaction. Okay? Well, you know, it is given. Sorry, it is given here. We assume the second step of the mechanism is the rate determining step. That's the slow reaction. First step is the fast equilibrium step. Okay, that's fine. I didn't read far enough ahead. Which of the following laws is predicted by this mechanism? Well, first of all, is that a valid mechanism? Well, let's add them together, right? If we add these two together, it should be equal to that. So this one cancels that one. This one is 1 plus 2 is 3. There's 3. This one is 1 and 1 is 2. So yeah, that passes the first step. Now we want to write the rate law in terms of the slow step, right? So remember, when we're talking about elementary steps in this mechanism, you can use the molecularity of the mechanism to determine the order. So you've got this one, there's one of them, and this one, there's one of them. So it would be the rate, let's go over here, rate equals some K times O3 to the first power times O, also to the first power. Okay? So what's wrong with this picture? We've got an intermediate in the rate law. You can't have that. The rate law has to have only reactants and or products of the overall reaction. Right? So we got to get rid of that O. Okay? So this one has a K value. We're going to make that one K2. That describes the rate for that reaction. This one has a K1 for that direction and a K minus 1 for that direction. All right? And what do we mean by equilibrium? Well, equilibrium means that the forward rate and the reverse rate are equal. So what's the rate expression for this one? K1 times O3 to the first order. And that's equal to the reverse rate, K minus 1, O2 to the first order, and O to the first order. Okay? Now, we need something to substitute here that includes only reactants or products from the overall reaction. So if we solve this one for that value, what do we get? In that case, we get O equals concentration. O equals these two divided into that one, K1 O3, divided by this one, K minus 1 O2. Okay? So now we have something we can substitute right here. All right, so let's take this one. Let me erase. Sorry. I'm going to have to erase these two. We've already got their rate expression, so we don't need them anymore.
He's still teaching, so I probably couldn't get there today.
Okay, rate equals K2 times O3. And then we substitute in this expression for that one. There we go. Okay. Now we've got an expression that has only reactants and products in it. So this rate expression can be combined so that all the K's are together. K2 times K1 over K minus 1. And then the rest of them are O3. Now O3 is to the second order. And O2 is actually to the minus 1 order. Why? Because it's in the denominator. And this whole expression condenses to K. Okay? So K times O3 to the second power times O2 to the minus 1 power is a valid expression of rate based upon that mechanism, which is C. Okay, that's how we got to that expression by way of substitution and by way of the slow step in the mechanism. That's the rate law that we should see experimentally determined for this reaction. If it's not, if we experimentally determine a rate law for this reaction that's different than that one, then that mechanism is false. Okay? That's just facts of life. All right. So that was 12, and we're out of time. I had one other one. Oh, shoot. Since I'm recording and there's nobody else here but me, I'm going to give you the last one I wanted to do, which is not in your review document, but I think it's very valuable. Okay. I'm going to have to draw a picture first. Let's see if I got, yeah, we're still on the screen. I'm going to have to draw you a picture. So let's say we have you're given a graph, and the graph looks like this. Yeah, looks like this. Okay, you got time here, and you got natural log here. All right, and you got a line that goes with it. Okay, now you've got let's say you got a formula, right? A formula for that line. The straight line equation. And it says y equals minus, let's make something up, minus 3 times 10 to the minus 2 x, and x is t. Let's put t in there. Let's do this. Log a. Yeah, that's better. And then plus 7 times 10 to the minus 5. Okay? Now, what can you say about this experiment from that graph? First thing you notice is it's plotted time against log of concentration. Right? So you know it's a kinetics experiment. You also know the order of the experiment in terms of A. Right? In terms of A, it's a natural log, so it has to be first order. So you can write the differential equation, rate equals some k times A to the first order. Okay, you know that. Can we put k in there? Yes, as a matter of fact, we can, because the slope equals negative k. So k is just this part right here. So the rate then is also equal to 3 times 10 to the minus 2 concentration A to the first power. Right? So there you've written your differential rate law from that graph. Now, do we know what A0 is? We can figure it out, right? If this is first order, then that expression right there, that is equal to the natural log of A0. That's the intercept up here. This is the natural log of A0. So all you have to do is say e to the 7 times 10 to the minus 5, and you got your A0, your starting concentration. Right? So if you say 7 exponent 5, change sign, and then say e to that value, we have, it's basically 1. That was purely accidental. So A0 equals 1 molar. Okay, all of that you can get from that graph. All you need is to understand what's being plotted and to see the straight line equation given, and you can extract all that information. You could do the same thing if it was 1 over A, right? It would just be a different formula up here. And if it were that, if it were second order, that line would be which way? That way, positive slope. Okay, that's all I wanted to say, is graph interpretation. And since there's nobody left here, I'm just talking to myself. That'll be the end of today's class. So whoever's watching this, I hope your weekend is studious, full of chemistry. All right, so let's see. I'll stop the video and we're done.